Okay, class, welcome back. This is lecture 16. Today we're talking about Laplace transforms. So today I'm wearing a headband. I don't know if you could see, but it's basically because what we're doing today is a bit like jutsu, if you know what Naruto is. This stuff is like magic. So we're going to basically be doing some cool anime magic to solve differential equations. All right, so let's get started. Given a function, so we're going to be using t as our input variable in this section, just because the Laplace transform comes up a lot in applications where you think of the input variable as time. And also because we just want to have our variable only defined for t being bigger than or equal to 0 anyway, which is good for time. So that's why we're going to call it t from now on. Okay, so if you have a function of time, then what you can do is you can transform it into something else. And that's the idea behind a Laplace transform is you take your function, you transform it into something else using this magical process that is really cool. And then you go from there. So the Laplace transform, I don't know how capitalized it doesn't have to be capitalized, but Laplace does, named after a famous mathematician, of f of t is, so it's a couple different notations. First, I'll write it like this. So you use L, but it's a fancy script L that I can't draw, so I'm just drawing a capital L. But in books, you'll see a fancy version of this L. You stick your function inside these curly brackets. Very hard to draw curly brackets. You have to have a PhD in math to draw a good one, but try your best. That's okay. So I'm really good at drawing them. Look at that. Other side's a bit harder, but that's okay. But try your best to draw cool curly braces like that. Any case, the Laplace transform is, that's the name of it, but what is it? It's the integral from 0 to infinity. You take your function and you multiply it by e to the negative, and we introduce this other variable s t. So you take e to the negative st, multiply it by the function of time that you're dealing with, and voila, that's the Laplace transform of f of t. So what's going on is you get a function of this new variable s. So often in applications, s you can think of as frequency, but we may or may not get to that, but that's okay. The point is you do get this other function of another variable s, and so what that means is sometimes you call this capital F of little s, like that. It's another name for the Laplace transform. Okay, and this looks very complicated, but we'll do some examples and see that it actually is complicated, but not as complicated as it seems. And then just to be very careful, if you don't remember how improper integrals work, where you have an infinite end of one of them, then you got to be careful about when the integral exists. But we're gonna not worry about that too much. Okay, so let's just calculate some of these bad boys real quick, just to get some practice calculating Laplace transforms before we deal with how to actually use them for anything. Okay, so here's perfectly reasonable function of time, the constant function 1. Let's determine the Laplace transform of 1. Okay. Let me just write f of t actually. Okay. So the solution is to just use this thing. So the Laplace transform of 1 is the integral from 0 to infinity e to negative st times the function that you're transforming, which is 1 in this case, dt. And then when we calculate this, what we're doing, I should have probably set it up here, is we're holding s constant. So it is a variable, so you get this function of s, but we're holding s constant as we do the integral. So it acts like a number. And then the other thing to be wary of is you have to remember, how do I do the integral if there's an infinity on one of these? Well, we might get lazy, but I'll do it technically correct on the first time. So what you're supposed to do is you're supposed to take the limit as another variable approaches infinity, and then you change infinity into that variable. So I'll do it properly, at least this time. Okay, so now I can do the integral. So what's the integral of e to the negative st? If I'm holding s as a constant, it's just e to the negative st divided by negative s. And now it's a definite integral, so I'm going from 0 to b. So then I plug in b, and I plug in 0, and I subtract for t. I'm plugging it in for t. And then what's going on here? Well, this, I don't know why I changed it to bs. Well, that becomes that. Okay, so what's happening as b goes to infinity? Well, as b goes to infinity, as long as s is positive, this is when this integral will make sense. So I have to now stipulate that s needs to be a positive number, because otherwise this will diverge. It'll go to infinity. But as long as s is positive, then as b gets really, really big, this divides by a really tiny number. And so this goes towards 0. So then I just get 1 over s, because these two negatives are canceling over there. So that's the Laplace transform of 1. But it's only viable when s is greater than 0. Okay, let's do another one. So let's just think about the function f of t equals t. So then the Laplace transform of this function, it's going to be a little bit more complicated. So this doesn't change, e to the negative st. Now this is times t dt. And now we're going to have to bring in integration by parts to do this integral, unfortunately. So I'm going to do the little tabular method shortcut. So I'm going to stick one function, which is t on the derivative side and one on the integral side. And then I'm going to do plus minus plus, and then I'm going to take derivatives on the left, integrals on the right. If you don't know this technique, you can just do integration by parts the long way. And good luck with that. That'll take you forever, but you can do it. Okay, then the next integral would be e to the negative st over the negatives would cancel. And then the answer is this. So this is just going to be negative t e to the negative st over s. So that's this times this. Then I add and do this times this. There's a negative 1 times e to the negative st over s squared. And now I'm going to just skip the little limit stuff and just write it as 0 to infinity. But it's secretly changing the variable to b, taking the limit as b goes to infinity. Okay, so then what happens? So let's see. Okay, so as t goes to infinity, what happens? This goes towards 0. Because I'm dividing by e to the t, and that'll get really big. It's much bigger than t, which is on the top, so that'll go towards 0. And then so will this one. So I'm really just getting a big giant 0 minus, and now I'm plugging in 0. So when I plug in 0 for t, that first guy is still going to be 0. And then I plug 0 in here, and I get e to the 0 over s squared. And so in the end, I'm just going to get 1 over s squared. So those minuses will cancel. E to the 0 is 1. And so that's the Laplace transform of t. Okay, so far so good, I hope. I'll do a couple more by hand, but in general, what you do is you look at a previously calculated table to help you out, so you don't have to do all this every single time. Because for us, the Laplace transform is just a tool to use. So our main goal is not just to calculate them, but it is good to practice a little bit. Before you use the hammer, you should practice using the hammer, I guess, if that makes sense. Okay, so let's do this one. Ignore my bad analogy. All right, so the Laplace transform of e to the negative 3t is, keep that the same. Now that's e to the negative 3t. This one will be a little bit easier actually, because here I can combine because the base is the same, and I get e to the minus, how do I want to do it? I'll do it like this. And then I will remember that I'm thinking of s as a constant, t is the variable. I can just take out a t like that. And now I could do u sub if I want, but it's just going to end up, because negative s minus 3 is just a number in this situation. It's just going to be e to the same thing. I'm going to take that negative out, actually, write it like that, divided by the number next to the t, 0 to infinity. Again, that's really a limit as b goes to infinity, but I'm doing a little quick shortcut. And when I think of t as going to infinity, the first thing is going to go to 0 again. Then I subtract and I plug in 0. And I get e to the 0 over negative s plus 3. So I'm just going to get 1 over s plus 3. And I forgot on the second example, but this is only viable for s bigger than negative 3. Why is that? Well, it's really because back here, I need this thing to stay negative, so that as t goes to infinity, I divide by infinity and make the whole thing go to 0. Okay, so that's why we need that. All right, so that is Laplace transform of e to the negative 3t. Guess I can do one more. I don't really want to because it's big. Okay, I'll do it. All right, Laplace transform of sine of 2t. We're gonna have to bring in some integration by parts again, but even fancier version of integration by parts. Okay, so e to the negative st sine of 2t dt. Integration by parts. I'm going to use my fancy table technique, and I'm going to stick the sine of 2t on the left and the e to the negative st on the right. And then it's plus, minus, like that. And I take derivatives on the left. So derivative of sine of 2t is 2 cosine of 2t. And then derivative of cosine of 2t is negative, and I bring out another 2, sine of 2t, and I think I can leave it there because of the trick I'm about to use. Integral of e to the negative st is e to the negative st divided by negative s, and then I integrate again. E to the negative st over s squared, because I'm going to divide by another negative s. I have to pause for 1 second. Okay, and then where was I? Okay, so I have to multiply diagonally. But this time the derivatives don't go away. So this will just go on forever if I do this. So the other way this technique works is if I go across, then I keep the integral sign. So this integral becomes, let's see. So I have sine 2t e to the negative st divided by s, and I have a negative from that s on the bottom, minus, and then I have a 2 cosine of 2t e to the negative st over s squared, and then plus a negative 4, but now I keep the integral because I'm going across, sine of 2t e to the negative st over s squared dt, 0 to infinity. And these ones are already evaluated, so they're going from 0 to infinity. Okay. So then the trick to this type of integral is remembering that this looks suspiciously like this. And so then I'm going to add my negative 4 integral of this giant thing to the left side. So then I get 4, and the s squared I'm going to take out to the 4 here. So I'm adding that to the left side where this other integral already was. And that equals this other stuff that's been evaluated already. So negative sine 2te negative st over s 0 to infinity minus 2 cosine 2t e to the negative st over s squared, also from 0 to infinity. So then I could factor this integral out and divide by the 4 over s squared, and that will solve for it. But let's figure out this right side first. So on the right side, what is going on here? So as t goes to infinity here, this will go to 0 and make everything go to 0. Then I subtract and I plug in 0, but then sine of 0 is 0. So that'll just be 0 minus 0. Minus, and then over here, when I plug in infinity, this will go to 0. I subtract. And now when I plug in 0, that'll go to 1. Cosine of 0 is 1. So I just get 2 over s squared. So this right side is really just 2 over s squared. And this left side is really just 4 over s squared plus 1. Oops. And then I've factored out this integral that I was trying to solve for in the first place. I don't know why I wrote the sign first this time. Whoops. Okay, I'll flip it back. So then if I just divide by this 4 over s squared plus 1, then I'll be done. Let me put it back in the earlier form this time. So this is 2 over s squared. Let me change this 1 over here to an s squared over s squared, so that it becomes 4 plus s squared over s squared, so that when I multiply it across, it's s squared over 4 plus s squared. And then those will cancel. So I'm finally done. 2 over 4 plus s squared. So that is the Laplace transform of sine of 2t. Whoops, I changed this to a t, but there was a 2 there. 2t. Okay. That's the last one we're going to do. So next is some rules that will help us. So L is a linear transformation. So meaning it's got some good rules. Means if I have two functions added together, I can Laplace straight through that plus, so I can Laplace them separately, Laplace transform them separately, and then add versus add, and then Laplace. So here I'm Laplacing each one, and then I'm adding. That's what it means to be a linear transformation. One thing it means. The other is that constants can pop out. So if I have a number times a function, I can also pop that out of the Laplace transform, and that will save me some time, and this will save us lots of calculation time, because if I have a bunch of stuff added together, I can just do it by pieces. And if I have constants, I can just take them out. Okay. So that's going to come into play in a bit, but the next thing we need is where the magic really happens, which is thinking about what do Laplace transforms do to derivatives. So after all, we're going to have derivatives in our differential equations, so this should hopefully help us with that. And it will. This is where the jutsu comes in. This would be Laplace jutsu, I think, is what it would be called in Naruto. So let's see. Okay, so if I have a function and its derivative then, as it turns out, the Laplace transform of the derivative can be written using the Laplace transform of just the function somehow. And that's what we're going to figure out. So what this is saying is that the Laplace transform somehow gets rid of derivatives. So if you have a derivative, you take the Laplace transform, it'll go away somehow, which is very good when it comes to differential equations. So let's see how this works. All right, so we're going to calculate the Laplace transform of f prime. And let's just use the definition. So we just stick it in here and see what happens. So once again, integration by parts is going to come into play. But it's a little bit trickier because we have to sort of think about the fundamental theorem of calculus a bit more than we want to usually. That'll come in a second. Okay, so here I will stick f prime of t on the right, where I take integrals, and I'll take this guy and put it on the left, where I take derivatives. Sorry, 1 second. Yeah, okay. So then what do we get here? So what is the integral of f prime? Well, it's just f, great. And what is the derivative? This guy, it's negative s e to the negative st, but then I have to do this plus or minus business. And I'm going to do this to calculate the integral. So it's going to be e to the negative st times f of t, 0 to infinity, plus, because these two negatives will cancel. And then I go across, so I keep the integral s e to the negative st times f of t dt, which is really good because what is this thing? Well, s is a constant. I can just take it out. But what is this thing that's left here? Isn't this just the Laplace transform of f of t? It is. So like I said, I will find the Laplace transform of f prime, and it will somehow involve the Laplace transform of f, and this is exactly what happens. But what about this other stuff? Well, as t goes to infinity, what's going to happen here? Well, as we have some restrictions. So f of t needs to not get really big, basically, because this guy is going to shrink to 0. F of t needs to somehow not grow faster than this one shrinks. So that is a restriction, but we're not going to worry too much about it. So it's going to go to 0 minus, and then if you plug in 0, this just becomes f of 0 times e to the 0, which is 1. And so you get this. So interestingly, the Laplace transform of the derivative is the Laplace transform of the function times s, but then plus you have to know what the function does at 0. So let me just write it this way because people like to write the Laplace transform part first. Oh wait, there should be a negative here. Close one. So this is the formula for the derivative. So basically it turns your derivative into multiplication by the variable s. But then you have to also know what your function does at 0. Okay, so then if I do the second derivative, I should sort of be able to establish the pattern. So let's do that. So then what is the Laplace transform of the second derivative? So you can sort of use integration by parts the same way as before. So you're going to end up with this, and then you're going to do the integral of the f double prime and just leave you with f prime from 0 to infinity. And then you're still going to have this s times the integral of 0 to infinity e to the negative st. But now this is going to be f prime of t. Just it's the same pattern as up here. Because now I'm one derivative up, so this is one derivative up from last time. Last time it was just f of t, f of t. Now it's f primes. But this is good. So what's going on here is that the left side, again, when you plug in infinity, it's going to go to 0 and then minus, and you plug in 0 for t, and you get that. That sort of looks like last time, but now there's a prime. And here, what we're going to do is we're going to notice this is just the Laplace transform of the derivative by definition, because you're just plugging in the derivative to that spot there. So this is really just this. And here's how we sort of build this recursion thing. Because that I already calculated just a second ago up here. So now I'm going to plug that in there. So I get s times this new thing. Distribute the s and rearrange a little bit. We get s squared. So that the second derivative gives us 2 s's. So every time we take a derivative, the idea is that we get a multiplication by s of the original. There should be no prime anymore. The original function. But then you also get, because you have to distribute this s in, you also get an s times your f of 0, but then your first derivative does not have an s. So this is the Laplace transform of the second derivative, and we can sort of see the pattern growing. So let's see if we can guess the third derivative. So there's going to be s cubed times the Laplace transform of the original function. And then this f of 0 is now going to get another s on it. The derivative is going to get one s, and then the second derivative is going to get no s's. So you need to know, in order to calculate the Laplace transform of the third derivative, you need to know where 0 goes in the function and its derivative and its second derivative. So you need the previous derivatives. So then, in general, you can see the pattern. I'm not going to need the big old general pattern. So maybe I won't write it, but maybe I'll instead just see how this is used. Let's do that. So how can we use this to solve a differential equation? That's the big important thing. So we're using this just as a tool to solve a differential equation. Well, differential equation involves derivatives. Let's, of course, start off with one we already know how to do. And so we could verify it if we wanted to. So for the Laplace transform to work on derivatives, you need to know these values. So what that means is we really need to solve an initial value problem. So I really got to tell you what 0 goes to, and for y of x and for y prime of x, in order for us to be able to use the Laplace transform. Okay, so what we do is we apply the Laplace transform. We basically turn our differential equation into an algebra problem. So because it's linear, I can just pull these constants out and put the Laplace transform through each thing. And now I can use what I just learned. So the Laplace transform of the second derivative is s squared times the Laplace transform of just the function minus s times y of 0, right? So I'm using this one right here, minus y prime of 0. And then the Laplace transform of the derivative is just s times the Laplace transform of the function minus the function at 0 and then I have 3 times the Laplace transform. Now on the right side, we actually did this one earlier. So we already know that this is 2 over s squared plus 4. So luckily I did this earlier example. So where does this leave us? Well, let's plug in these initial conditions here. And what we're going to do is we're going to solve for the Laplace transform of y. So the idea is that I have my my function y of t or y of x. I guess it's y of t in this situation because I use t over here. And I have its Laplace transform. And if I could solve for it, then maybe I'll be able to solve for the differential equation. Okay, so anyway, I'm going to plug these guys in. So y of 0 is 1. Y prime of 0 is 3. Let's distribute this 2 in here. Oops, sorry, it's a 2, not an s. 2 over s squared plus 4. So now let's see. I will, everything that has the Laplace transform of y, so these three terms, I'll stick together and factor it out. So let's do that. So then I have an s squared plus 2s plus 3. And then on everything else, I will just subtract over. So I guess that just leaves these two. So that would be what? Minus, would be plus s. And then I have a minus 3 and a minus 2 is a minus 5. So I add that 5 to the other side. And then if I divide by this thing, I'm going to do it like this. Keep my algebra nice and clean. Then what is this saying? Well, what it's saying is that although I don't know what y of t is, I do know what its Laplace transform is. So if I somehow knew which function transformed into this thing on the right, then I would be done. So to finish, what you would need to do is somehow undo the Laplace transform. The idea is something like this. Well, let's say, think of something simpler. So what if I ended up with L of y equals 1 over s instead, something much simpler? Well, earlier, we already figured out that the Laplace transform of 1 was 1 over s. So this would tell us that the function we were looking for was just the function 1. And that's the idea here, except it's much more complicated. We're looking for which function gets transformed into this big giant monster. It's not just 1, unfortunately. And so this brings us to the idea of the inverse Laplace transform. So the idea is that if you know that some function of s is the Laplace transform of something else, so we're not going to finish that problem. Then you can go backwards. So then what that means is f of t is the inverse of big F of s. Okay. And you can write it as L to the -1, because -1 always stands for inverse of f of s equals f of t. So calculating, we don't really calculate these. We just look at a table and see if we recognize what's going on based on previous work. So that's what we're going to do here. We're not going to really calculate these. So let's just do this. What's the inverse transform of 1 over s? Well, like I said earlier, that's going to be 1. And it's not because I've calculated anything. It's because I already know that the Laplace transform of 1 is 1 over s. So I'm literally just looking at it and determining the answer, not calculating anything. So we can only do the ones we've already figured out the other direction for, is then the problem. So for example, another one we did earlier gave us 1 over s squared. So the inverse of this is t. And again, it's not because I actually calculated anything. It's because earlier I calculated the Laplace transform of t, and that was 1 over s squared. Just for completion, you can do the rest that we got earlier. The inverse Laplace transform of 1 over s plus 3 is e to the negative 3t, because earlier I calculated that. Okay, so solving these differential equations is a bit complicated, because what this means is that when we have something big like this on the right-hand side, we have to somehow work and massage it with algebra to see how it's actually the Laplace transform of something we already know. We're not going to actually calculate a Laplace, an inverse Laplace transform. Okay. So you'll see examples of that on the lecture problems. But that's it for today. So see you next time.